In this video, we will have a look at the Drag Your GAN paper that allows us to easily edit images via drag and drop. While some people have already called this the end of Photoshop, I certainly don't believe that because there's still some limitations to this approach. However, we will have a look at all of it. We will have a look at the paper, re-implement the paper in PyTorch, edit our own images, and in between, I will also unveil some limitations of this approach. So today, we will gain a deep understanding about the Drag Your GAN paper. Hi and welcome back, guys. I know it has been a long time since my last video. Sincere apologies for that. I even got asked if everything is okay with me. Yes, please don't worry, I'm fine. I just have been very busy the last 2 months, as life sometimes is. And yeah, I even got this comment from Jimmy who asked if everything is fine and he misses my content, which I really appreciate. Thank you so much. All your comments always motivate me to keep going, to create new videos, so please keep them coming. I always appreciate them. Unfortunately, it's hard for me to reply to all of them, but I feel like I can quite confidently say I've read all your comments so far. So please never hesitate to give me your feedback, ideas, anything, how you like the video. I am always happy to hear your feedback about my videos. And yeah, also all your nice words, they really mean a lot to me. So thank you for that. And now let's head back to the Drag Your GAN paper. And honestly, I didn't have much experience with GANs before reading the Drag Your GAN paper, because I felt like the last 1.5 years, the majority of people have focused on diffusion models, which are superior and generating high quality images. But as we can see with this work, GANs can also have advantages when it comes to image editing and having a better control over the image editing process. And because of this, besides reading the Drag Your GAN paper, I also read some other papers to really gain some fundamental knowledge about GANs. And once I had collected all the needed knowledge, it was super easy for me to understand the Drag Your GAN paper. While the first time I read it, I had some issues and couldn't follow all of it. And because of this, I decided to also give you a brief history about GANs. And with this brief history, you will be able to easily understand the Drag Your GAN paper. Okay, should we start? Let's go. Okay, let's first recap how a generative adversarial network actually looks like. And here we can see an example of it, while we have here our generator, the generative part, and our discriminator, the discriminative part. And we can imagine this as our generator takes a low dimensional input vector and maps it to a high dimensional realistic output image, which could look like this one. And our discriminator then decides if this is a realistic image or not. So our discriminator basically sees the images generated by our generator and then has to decide if this image by the generator is a real one or not. And this is basically a little bit like a game between the two of them. That's also why it's called adversarial, because they are playing against each other, and the training is in a way alternating. So first we freeze the weights of our generator so that only the discriminator gets updated, and then once we have trained our discriminator a little bit better, then we freeze the weights of the discriminator, and then our generator gets optimized and it gets basically better at generating images. And another way we can think of the discriminator is basically as the perfect loss function, because it's very hard for us humans to describe in a mathematical function how a realistic image should look like, especially in a mathematical function that is easy computable and differentiable. So basically, since this is like kind of like a complex task, we just leave it to the discriminator to learn this perfect loss function. And then using this perfect loss function, our generator learns how to generate highly realistic output images. And another property that we can see here, our generator gets a low dimensional input vector and maps this input vector to an output image. Yeah, and you might be thinking, why is he talking so much about this low dimensional input vector? This will become very important for the Drag Your GAN paper. And what we can basically imagine, as I said, the generator is a mapping function in a way from a low dimensional input vector to a high dimensional output image. And another way to think of this is to look at this paper that we can see here, which is basically a 2D subspace, and by bending and folding it, we can basically transform it into a way different representation or shape, as you can see here, right? And now let's imagine this will be our space of all possible output images. And in there are a lot of noisy images that don't look realistic at all. Maybe you can refer this as if your TV has a broken connection. Maybe at least my older audience can refer to this. And now imagine this will be a realistic output image, this will be one, this will be one. So what we're basically learning here is called an image manifold. We're trying to bend and transform a lower dimensional input space so that we can map our inputs only to realistic output images. So the generator basically learns this image manifold during training. And another property that often occurs is that neighboring input vectors that are also called latents correspond to images that are visually similar in the output basically. And by manipulating certain elements in the input vector, we can then basically add it in our output images, something like the pose, the hairstyle, if the eyes are open or closed, which is a very important property for the Drag Your GAN paper, which you will see later why. And one model which is exploiting this even further is the StyleGAN or StyleGAN 2 model. And the whole assumption of this model is that we can basically reconstruct an output image just by applying a certain set or amount of styles to the image. What does that exactly mean? So as you could have seen here, we're taking our input vector and mapping it to a way higher dimensional space, right? And the problem here is that those output images are directly related to our input vector. So let's say in our training data or in our training data distribution, we had a lot of images with man and short hairs, while we only have a few men with long hairs. And the problem with this is that the model will be way better at generating images with man and short hair than man with long hair. But ideally, our model should also be able to generate man with long hair in a good style or in a good way. And to overcome this, the StyleGAN model introduced something which is an intermediate representation. So instead of directly working in our input vector, we have a mapping network in between that maps our input vector to an intermediate latent space, which is actually a vector of the same dimension as the input vector, but it just takes away the direct dependency of our input vector to the output image. And I found the reason for this approach very well explained in another Medium article, which I just quote here. The goal is to encode the input vector into an intermediate vector whose different elements control different visual features. This is a non-trivial process since the ability to control visual features with the input vector is limited, as it must follow the probability density of the training data, for example the man with short or long hair. For example, if images of people with black hair are common in the dataset, then more input values will be mapped to that feature. As a result, the model isn't capable of mapping parts of the input, elements in the vector, to features. Features could be, for example, pose, hairstyle, eyes opened or closed, a phenomenon called feature entanglement. However, by using another neural network, the model can generate a vector that doesn't have to follow the training data distribution and can reduce the correlation between features. So in a way, in our intermediate representation, we can better cover features that are not as often represented in our training data distribution. So we make them less correlated or less dependent on the training data distribution. And now let's have a look again at the StyleGAN architecture. So first we map our input vector to an intermediate representation, which is called W, and then by affine transformations, which could be, for example, a fully connected layer, we then map those to different styles and apply them within the individual blocks of our network. So, for example, one block is the 4x4 dimension, then the 8x8, and if we generate a 1024 times 1024 image, we would have here 7 more blocks. So in total, our network would have 9 of those blocks, while we apply 2 styles per block. So what those affine transformations basically do is, in our intermediate input vector, which is basically an abstraction of our different styles, we then learn a transformation that allows us to apply certain styles at a different blocks level. So the impact of those different styles on the generation of our output vector has also different effects depending on the scale. So by scale I mean if it's like 4x4 or 8x8 or in the higher resolution blocks already. So the authors distinguish the effect of the styles in 3 different categories. So we can see here coarse, which is 4x4 to 8x8, where we have high-level aspects such as pose, general hairstyle, face shape and eyeglasses, while we have middle from 16x16 to 32x32, and here we have smaller scale facial features, hairstyle, eyes open and close. So this will be a finer hairstyle, eyes open or closed. And then in the upper higher resolution generator blocks, the styles only have an impact on color scheme and microstructure, which are very subtle. And since this was all pretty dry and the authors created a really great visualization to better understand the impact of those different styles, I would say let's have a look at them to better understand what this actually means, like how the different styles on the individual scales have an impact on the generating process. And before we do so, there's one thing that I would really like to point out, and this is that the styles can be manipulated individually, allowing us to change attributes like age, gender, pose, and expression, which is basically the foundation for the Drag Your GAN paper, which I will show you after this. And now on the left hand side we can see the styles, so we see the individual pictures, and out of those pictures we basically take the styles of those pictures and apply them to the picture on the right hand side, the bigger picture. And as discussed before, we have 3 different categories of styles, so we have the coarse, middle, and fine styles. And now we can see that the coarse styles impact high-level aspects like the pose of the person, the facial shape, or the hairstyle, while the middle styles are more impacting smaller scale facial features, especially if we're paying attention to the eyes in this example, or also to the hairstyle. And now for the fine styles, we can see that the fine styles only have impact on the color scheme and the microstructure of the image. Okay, and after this brief or not so brief introduction to GANs, we now can finally have a look at the Drag Your GAN paper, which you can see here. And yeah, why was this introduction so long about the GANs? This paper is really, or the whole Drag Your GAN paper really relies on the StyleGAN model or generator. As I also describe here, our study is based on the StyleGAN 2 architecture, and it's really important to have an understanding for the StyleGAN 2 generator to really understand what's going on in this paper and why this approach works. That's why I spent so much time with you going through all this, because I also first read this paper and then read the StyleGAN paper, and I wouldn't recommend to do it this way. So, you know, in this video I already gave you, in my opinion, the best structure to understand this paper. And to be honest, in this paper there are actually 2 major contributions or 2 major techniques that help us to really edit images just via drag and drop. So we select our handle points, multiple in our picture, and select where we would like them to move. And then the whole thing is just an optimization technique. So we don't even need to fine-tune or train a new GAN or I don't know, any kind of model. We really just optimize our intermediate latent vector W, which you saw earlier in the StyleGAN architecture, but more on that later. So what are those 2 major techniques that this paper proposes? The first one is the motion supervision, and the second one is a point tracking. But let's start with the motion supervision. And the key idea here is that the intermediate features of the generator of the StyleGAN 2 architecture are very discriminative, such that a simple loss suffices to supervise the motion. So what this motion supervision proposes is that we can take the feature maps after the 6th layer or 6th block of the StyleGAN 2 architecture, which we saw here. So this is basically the first, the second in our network. So we have a resolution of, I think it should be 256 times 256. And based on those feature maps, which according to the authors have performed the best among all features due to good trade-off between resolution and discriminativeness. And then we resize those feature maps, which have a resolution of 256, to have the same resolution as the final image. And this depends, the StyleGAN has different versions, but let's say if we're interested in the human faces that we also saw before in that video, then it will be an output resolution of 1024 pixels. So we would use bilinear interpolation to just upsample the feature maps after the 6th block to this size. And what we would then do is select our handle points, which we could see here in this picture as a red handle point, and we have our target point, this one. Here we only have 1, but technically we can, I don't know, I think there's no upper limit, so you can use as many as you want. The idea then is to calculate a normalized direction vector, which is this one. So what does this exactly mean? TI is basically our target point, and then we have PI, which is our handle point, and with this we just calculate a normalized vector that is pointing from our handle point to our target point. So this way we'll use this direction vector here to basically move our handle point towards our target. And how can we do that? First we need to figure out what this QI is. And for this we can see that QI are all elements or pixels inside this omega-1, and we pass our handle point I and at a distance R1. And I felt like this is described a little bit more complicated than it actually needs to be in a way. So in practice R1 is just set to 3, so we just take all neighboring pixels with a distance less than 3, and to just make it easier to understand, I made this very easy sketch here. So you can see this is our handle point, And in omega 1 are all those pixels that have a distance less than 3. So we can see here the distance is 2, here's 2. I think this should also be in, so it's not circular. So we also consider those. So we just have an image patch. So we can think of omega 1 as just an image patch, and all QIs are in this image patch. So elements in this. So just like neighboring pixels, which makes this way easier to understand. And we remember our feature maps after the 6th block of the DragGAN generator. And we not only have one feature map, but we have actually 128 in a row. So imagine we have a book of 126 pages, and we would chop off a small piece, like basically at 1 pixel. Then we have, like in depth, basically 1 vector. So this is a vector, and this is also a vector. But since our direction vector that is pointing from our handle point to our target point is normalized, we don't have an integer here, which doesn't allow us to access or index our feature maps, because we basically need integer pixels to index the feature maps. So what we're doing here, we need bilinear interpolation. And then for both of them, we calculate the L1 distance, which is just to measure how far those two are away from each other. And this we then do for all different handle points. So we can see this is like a summation for one handle point, and here we iterate over n, the number of handle points we have. So our loss just calculates for each handle point. We just take the handle point right now. We basically calculate a version that is slightly moved towards our target point, which could be, for example, here. And we calculate the difference between the two of them, and this is our loss. And one term that we haven't talked about in this loss function is the second term, this one here. I found this equation a little bit hard to read because both some symbols are just denoted for this expression. So we basically could put parentheses around those two here, because or just replace this one before both some symbols, because this term is just for our mask. So what we're seeing here, the F0 are our initial feature maps of the initial image, and these are the feature maps of the updated latent code. So during our optimization, those feature maps here will get updated while those remain the same the whole time. So what we are basically calculating here, similar to what we're doing here, we're just calculating the distance. How much have those feature maps changed during our optimization? And we multiply this with our mask, which is a binary mask. So for example, we would just highlight a certain area. For example, that could be the face, and all the values in our mask where the face is would be 1. So basically this expression would be a 0, and then the whole distance would be 0 because we multiply it by 0. And what is the impact or the effect of this? So within our mask, we don't want to penalize the loss for any changes in the feature maps, while outside the mask, this is actually the whole reason why we introduced the mask, we don't want any changes. What this term actually says is basically the background without the mask should remain the same and shouldn't be changed at all. So only pixels inside the mask should be updated and changed. And this is just a scaling parameter, or how much we want to penalize the generator for changing pixels in the background or the feature maps in the background. And then we use this loss and basically propagate the loss back into our model inside the generator, while all the weights of our generator are frozen. So the only thing that can be updated is our intermediate latent code W. So this is basically the whole assumption of this. This is also why I in the start said like, oh, imagine like an image manifold. We have a low dimensional input vector and then have a high resolution output image. And this is basically just a mapping. So what we're doing, we're propagating through our mapping all the errors or the loss that we have calculated here to optimize our low dimensional input vector or our low dimensional intermediate latent that we have in our DragGAN architecture. We can just use a loss function, propagate it back, and this way we optimize our intermediate latent and are able to change the pose of a person. And we're not doing this at once. Basically, we only do the motion supervision once, but we do multiple steps. And one thing that maybe now you could think of is, okay, we have updated our intermediate latent code. So for example, we're taking me right now. Here's our handle point, so it's my nose, and we want my nose to move to this direction. So what I would do then is, like, after one motion supervision, maybe I look a little bit like this, but eventually I would look like this, right? So my nose is a little bit shifting, while we can see here our PI is technically not updated, right? It remains at the same place, but to guarantee that our small steps work and our small updates are done at the right direction. For example, let's imagine I move my nose and our handle point remains here. So at some point, those updates will be wrong, right? Because we would start updating, for example, my cheek here instead of my nose. And because of this, we need the point tracking, which allows us to track our selected handle points in a way. And one more time, there are approaches that are very complex and, for example, need neural networks to track those points. And once again, this paper does solely rely on the discriminativeness of the intermediate feature maps of the DragGAN architecture, which is very, the whole paper, I really like it. It's different. It's not like we're training a model or something. It's just very clever, very smart. But if you know the DragGAN architecture, it's also very easy to understand. Yes, and this time we need to keep in mind for the point tracking, the motion supervision for this iteration has already taken place. So we're working with an updated or new latent code, new feature maps, and also new image, because they are all already slightly moved towards our target point. So I'll stick to my face basically being moved to this direction. And what we're doing then, first we need to kind of store our initial handle point or the feature maps of our initial handle point. So F0 here are the feature maps after the 6th layer of this DragGAN 2 generator of our initial image. So for example, where my face is right now, centered. So and now we would take the feature map right from my nose here. And we will always use them, like we can see here, the F1, to compare. So even if my face is somewhere here or here, we would still compare with this initial feature map or feature vector of my nose to find my nose again at this point here. So we're trying to find this initial handle point that we had here in this updated image. So for example, now my head is moved to this direction, and ideally what our point tracking technique would do is find my nose at this location here. And what we do then is, again, we have an image patch or a feature patch around our current handle point. So this PI gets updated throughout our iterations. And again, we have an omega with this expression. And what this actually means is before we had a 5x5 feature patch, and this time it's 11x11. So the R2 here is 12. So we have an 11x11 feature patch around our current PI, and you can see this is in the dimensionality way bigger than this. And out of all those individual pixels here, so our feature maps are way bigger, which indicate those 3 points. We compare the closest neighbor. So which of those feature vectors in here are closest to the feature vector of our initial handle point, which was the Fi. So basically, now let's say we are here, we have a small window around my nose, and we try to find the point, which would be the tip of my nose, that is the closest to our initial point, which was here, this feature vector basically. And that's what we're iteratively are doing. So first we slightly move our handle points towards our target points, and then we relocate our handle points so that we can use them in the next iteration so that they're accurate again in our motion supervision technique, because here the omega 1 patches rely on an accurate position of our handle points that are getting updated in the point tracking technique. So basically what we're then doing, first motion supervision, point tracking, and it's like a loop. Do it again and do it again. And after the authors say like it takes 30 to 200 iterations in their experiments to basically reach all their target points from their handle points. And that's the whole, I would say, the whole magic behind the paper. And now let's just implement it ourselves. So this is the official repository for the DragGAN paper, and the code will be released, I think somewhere it was stated, code will be released in June. But I found a different implementation, and I just tried to pick the essential pieces of code, put them together in a Colab notebook, so we can basically go through and understand how we can code the Drag Your GAN paper ourselves. And that's what we're doing now. So we go through this. First, I would like to give credit, one, to the authors of the Drag Your GAN paper, of course. also to the authors of the DragGAN model. Also, the DragGAN was only implemented in TensorFlow, so there is a PyTorch implementation. So also thanks to Kim Seong-yeon. That's halfway pronounced correctly. And last but not least, also to the author of the Drag Your GAN implementation that you can find here. And yeah, what do we need to do to re-implement the Drag Your GAN paper? First, I basically broke it down into a pseudo code. First, we need to generate our latent code Z. Then we need to map the Z to an intermediate latent code W. What we then need to do is to generate the feature maps of the 6th layer of this DragGAN 2 generator. Then of course we need to define our handle and target points via drag and drop. Yeah, this point I skipped in this tutorial. We will just do it manually, but yeah, ideally for better editing you would do drag and drop. And then, as the whole magic of the Drag Your GAN paper, we will iteratively optimize our latent code W with motion supervision and point tracking. And at the end, of course, I will show you the edited images and we will see how this whole approach works. And I will also show you the limitations, because the demos look really, really cool, but there are also some limitations that we definitely should be aware of. So don't miss out on them. Okay. And first what we're going to do is to install the DragGAN 2 model, or as we saw here, the PyTorch implementation of DragGAN 2 by cloning the repository and installing required modules. So I'll just execute and run this one. And in the meantime, yeah, I did a small customization of the DragGAN 2 generator just because in this in the implementation here, in the forward process, we each time calculate the transformation of our input vector Z to our intermediate latent W, and yeah, we actually just need to do that once. So I split this into 2 pieces. That's actually the only thing what we're doing. So we are still importing that generator and just having one method that prepares our intermediate latent W, and the other one is just for the image generation process and also getting our feature maps inside the generator, so that we then use for our motion supervision and point tracking. Yeah, so this is basically our customized DragGAN 2 generator, and with this we can easily do the first 3 steps. So we can generate our latent code or initialize it by just having a random vector with a length 512, which basically is a 512 dimensional input vector. And then we map this input vector to the intermediate latent code W. And for this, yeah, we initialize our DragGAN 2 generator and then call the prepare function with our latent code Z. And what we will get back is our latent code W and noise, which, for example, if you have hairs or like freckles, they will not always be placed at the same position, or hairs will be a little bit more curly. So the noise is actually just responsible for adding a little bit of stochasticity. Oh my god, what a hard word. And what we will then do is to define our handle and target points. I would say I exclude the via drag and drop, as you will see here. So what we do is we manually define them. We have 2 handle points and 2 target points. Yeah, this is just a method or a util method to convert our tensor to an image so we can visualize our image, and this helps us to add the points that we selected to our image. And then we can see here how our initial image looks like, and here are handle points. Those are the blue ones are our target points. Here you can see, okay, this could be a little bit improved. I think this is pretty accurate already. One thing to know about the dataset or the generator, the positions of the eyes, I think, maybe also the mouth and the nose, are standardized in the dataset. So if you generate images often, they will be like in portray mode, basically like this person right now. I'm like, it's not a real person, just to point that out as well. And yeah, so what I will do, I will slightly move them a little bit to the left. So maybe just do 405 and see how that looks like. Yeah, and I think this a little bit better. Maybe I could do it even a little bit more, but I think that's fine. And what we'll try is to make this person really smile, because, you know, a smile is always for free, and yeah, has never put any harm to someone, right? Now that we have our handle and target points, it's already time to apply the optimization techniques, the motion supervision and the point tracking from the Drag Your GAN paper. And for this, what we will do is we need our function, a util function that helps us to find the neighbors. This is basically what we saw here. So either we give a distance which will be 3, so we get all surrounding pixels that are below 3, or we can give the 12 for R2, so we get our 11 times 11 patches. So what we could do, for example, is to call the getNeighbors function by calling getNeighbors. The position will be, let's say we put the position 10, 10, which is the x and y coordinate, and then a distance of 3. So we get our omega 1 for the position 10, 10, basically in our feature maps. And let's see. And here we can see, okay, it's not super easy to read, but we have like all the pixels around. So at the location 8, 8, 8, 9, 8, 10, 8, 11. So basically what we saw here, and that will be 10, 10, that will be 8, 8, for example, and that will be then 12, 12. Pretty sure we will find it here, right? Then next we need a util function for the bilinear interpolation to calculate this term, because the direction vector is normalized and doesn't have integer values, so we can't directly access those feature maps or the feature vectors inside the feature maps and have to interpolate them. So what does this exactly mean? This is pretty much a standard way to compute or to write a bilinear interpolation in code. So we have two directions in which we interpolate along the x-axis and the y-axis. So we have 4 different points. This might sound a little bit confusing, but this is basically, you can ask ChatGPT or just look it up. This is how bilinear interpolation is done. And I try to visualize it to make it easier for you to understand. So with regard to this term, this would be, for example, one specific point in our feature map. So we could think this is our QI and this is our direction vector, which is normalized. So the values in here would range from -1 to +1. And now let's say here's our target. So our direction vector would point from our QI to our target point, which is here. And since the components are still less than 1, our next pixel would be kind of this one, but not exactly. Actually, the value that we would like to access would lay between those two vectors. And what we're doing now, we basically interpolate. We take those 4 neighboring pixels, and depending on how much the digit of the direction vector contributes, one of those pixels will contribute more and one will less. Let's say both components of the direction vector would have 0.9, then this pixel or feature vector would influence our result of the bilinear interpolation way more than this one. But if it would be 0.1, this one would impact our result way more than this one. And with those two helping or util functions, we now can code the main part of the DragGAN paper, which we already discussed in theory. And now first, we will store our initial feature maps after the 6th layer of the initial image, which we use in the point tracking. And also we store the locations of our initial handle points. So we iterate over all handle points and then save their feature vector, so at their initial starting point of the handle points, in our P0 array here. Then we divide the latent that we earlier computed, which is our W intermediate latent, into 3 different parts. So one is the trainable latent, which are the feature maps before and including the 6th layer of this DragGAN generator, and all the feature maps afterwards are untrainable, so they will be frozen during our optimization, which we indicate by requires grad. Then we initialize our optimizer, which will be the ADAM optimizer, using this learning rate, which is also defined in the paper. And here we pass our latent trainable. And what we will then do is, this is basically a helping variable to figure out if we reached all our target points and can stop optimizing. Exactly, so then we break. And what we do here, we concatenate our 2 latents, the trainable one and the untrainable, to have a combined latent that we can pass to our generator to generate images, because we need all parts. Those are basically the set of styles, so the generator can generate the specific image for us. And it's important to do this within the loop, because this one gets optimized in each iteration. Here we can see we iterate now over our max iterations, and in each iteration our latent trainable gets optimized. So we need to redefine the latent in here. And then we will use the generator, pass our latent and the noise to generate our image and the feature maps after the 6th layer of the DragGAN generator. And we will initialize our loss with 0 in the start. And again, we also have here our variable that we set to true. So basically later we will look, are all our handle points closer than defined by a specific distance, which is 1 in our case, to our target points? And if so, then we can just stop optimizing our image because our handle points have reached our target points. What we do then is we define our PI and TI, so our handle points and target points. Here we compute the normalized direction vector pointing from our handle points to our target points, so PI to TI. As described, this is just we measure if the distance is closer than our defined value, and then we would break or stop our computation optimization because our handle points have reached the target points. And what we're doing then is we compute our neighbors, which we saw here. So this is basically our handle point right now, and we have all those neighboring in our, basically in our set. And then we iterate over this set. So this would be a QI, this would be QI. They are all included. So those will be in this green area, basically, or feature patch that we saw. So F2 are our feature maps after the 6th layer of the DragGAN2 generator. And now we use the Y coordinate and the X coordinate of our neighboring pixel. So we can extract the feature vector, which has a dimension of 128. And it's very important to detach this feature vector, because by detaching this one, we make sure that while optimizing using our loss, we optimize our intermediate latent in a way so that our feature, which is at our handle point, moves towards our target point and not from our target point towards our handle point. So this way we don't allow that the gradient flow through this feature vector here. Then, as earlier described, here we compute the bilinear interpolation by passing our feature maps, and then we add the direction vector with our QI and our feature patch. So basically this would be F1 and this one would be F2. And then we can just use the L1 loss, which we add for each QI. So we have this summation, basically, this part here covered in here. And yeah, I also did this for the mask, but since I don't have a graphical interface right now, I can't really make a mask. So we can basically skip this part because I won't use it. And then we set all gradients to 0 to prepare basically for a new round of backpropagation and gradient accumulation. And then we backpropagate the loss gradients through our model and then update our trainable latent by using the optimizer step. So that's basically the motion supervision. Yeah, already. So it's actually fairly easy. You can see it's not too much which I needed to code here. And then as a second step, we will code the point tracking. And for this, we use a Porch no grad because we don't want to update our trainable latent here. We just want to relocate our handle points because the trainable latent now got updated. So for example, my nose could be right now a little bit like this, and my handle point is wrong. So, we now want to relocate our handle points. And for this, first we again generate our image and the feature maps, and we iterate over all handle points and use those variables to figure out where our closest neighboring feature vector is. So we define again our PI, basically our handle point, get all neighbors. This time we get more neighbors, so we look within a bigger feature patch, which is of size 23 times 23. And first we here access our initial handle point, which we defined in the start, the P0. So that we had defined here of our initial image as well. So where the initial handle point in the initial image was, the Fi we have here. And then we just access our, I've called it F3, which is the neighboring pixel in our omega 2 or in our neighbors, and access there the feature vector. And then we again compute the L1 loss of those two, and then we just compare if our L1 distance smaller than the minimum that we have seen so far, and if so, we assign our minimum new with this L1 distance and also define our minimum X and minimum Y again. And by iterating over all our neighbors, we basically then find our closest neighbor and can then reassign the handle point with this closest neighbor that we have found. And that's basically it. By this we can basically retrack or relocate the handle point in the updated image. And after this, a new round in our loop continues. And as I said, this will be continued either until we reach the maximum of iterations, which we can state, or if all our handle points are closer to our target points then defined by a specific threshold, which in this case is 1. Yeah, and that's basically it. And what we're doing then, first I convert those to a tensor, the handle points and target points, which I earlier showed already here, those two. Then we will just call our DragGAN method, passing the generator, the latent, noise, our feature maps, the initial ones, and the defined handle points and target points. In each round, we will then take our sample, convert it to an image, so we can later create an animation. We add also our points to that image, so we can see how our handle points get updated and how they slightly move towards our target points. And then at the end, we will just save our edited image as well as an animation video to see our result. Okay, and I think now it's the big moment. It's time to shine, or to see, to fail if this works. So yeah, I'll give it a try. Alright, and now it's done. We can see it took 4 minutes and 21 seconds to optimize. I'm pretty sure that my code can be optimized, but I thought this would be the easiest understandable way. I hope you agree with me. Alright, and now I would say let's have a look at our animations, which we can find in our outputs folder. So here's the image and here's the animated video, and I already downloaded it, so I will show it to you here. So this is how we made our friend smile a little bit more. Yeah, what we can see here, I was hoping I could see a bigger smile. I think I would have needed even 2 more handle points so that his lower lips would stay or remain at the same position, so that it really forces the model to create a smile, because I feel like his whole, if we look at it again, I feel like his whole mouth moves a little bit upper. Well, I was hoping, we could see a bigger smile. But that's one of the limitations that we will anyway see with this paper. So the demos are really, really cool. But as soon as we're out of training distribution, we can quickly reach our limits. The one thing is that we're limited by the DragGAN generator. So the DragGAN generator is just trained on a certain type of, for example, portrait pictures or faces here. So we can't just take any image of us. And another thing is to even generate our intermediate latent or the initial latent for any picture of us, we need something that is called GAN inversion. And let's say like our replicated image with the GAN inversion won't be as precise as our real image. So to use this approach for your own pictures, there are definitely some burdens in between. This is not a replacement of Photoshop, because the GAN inversion itself is not 100% accurate and won't allow you to recreate any image. But for example, if I would take an image of me right now in this position, that could work pretty good. I'm not sure about the background, but at least the foreground, like my face, should be recreatable using the DragGAN model, and then we can basically edit my posture. So you could take a screenshot right now and make me smile, for example. That would work. And I don't want to say that this isn't cool at all. It's super impressive that we can edit images now in such a controllable manner via drag and drop. I just think it's important to also state what this model is not able to do, and the demos are really giving away a feeling that you're like, oh wow, they can do everything, but that's just not the reality. And one more point how I would like to show this is this video, where you can see there's like a huge distance for the nose, like a bigger range than for basically to make the person smile. I just had a small distance between handle and target point. And what this will force the model is something it's called basically out of training distribution, because the model doesn't know how it can generate a nose with this face basically being here, like the tip of the nose being here. And what I mean by this, you will see now, because this is a little bit disturbing. So now you can see this starts now getting out of training distribution, and now the model is basically guessing what it doesn't know. And yeah, here we can now basically see our handle point almost reach our target point. And yeah, this is not the image we were hoping for at all, which looks kind of disturbing. This is a limitation of this approach that I definitely wanted to show you. But as we saw before, it's definitely possible to edit images in a very new and interesting way via drag and drop using this approach. And I just think it's good to be aware of the limitations of the DragGAN paper. Alright, and that's it for today's video. I hope you liked it. Let me know in the comments, what are your thoughts on this video? what do you think about the Drag Your GAN paper? And also, would you be interested in me making another video about GAN inversion and how we can take our own images, convert them into a latent, and then we can edit our own images using the Drag Your GAN approach? Let me know in the comments if that will be something you will be interested in. And last but not least, I will be interested, did you like this code reimplementation or paper reimplementation? And should I do more videos like this? Yeah, I would be very interested if you guys enjoyed this and liked this. And if so, please let me know in the comments. And until then, have a good time and see you in the next video. Bye bye.